Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll discuss Perceptron, which is a classification algorithm. Perceptron is a binary classification algorithm. In this video, we'll cover 5 different components of this algorithm, just like any other machine learning algorithm. We'll also cover relevant mathematical details along with these components. Finally, we'll implement Perceptron from scratch in Python with NumPy library. So Perceptron is a basic machine learning algorithm that was motivated from neurons. It was invented back in 1958 by Frank Rosenblatt and was intended to be a machine rather than a program. Perceptron was meant to be a rough model of how individual neurons work in the brain. Let's look at the first component of Perceptron, that is training data, and this component is very similar to any other classification algorithm. The training data has two parts. One is a feature matrix X and label vector Y. Feature matrix contains n samples and m features, so it has shape of n, m, and the label vector has label for every sample. So label vector has n components. Since Perceptron can solve only binary classification problem, the label vector y has values which is either -1 or +1. Let's look at the second component, that is model, and the Perceptron model is inspired from the brain neurons. Let's look at the Perceptron model. So we have label y, and label y is obtained by applying a nonlinear activation function on the linear combination. Here we have written features as phi of x, which is after applying feature transformation. So this is more a generic way of writing the features. So we have features which are multiplied by a weight vector. So this is a linear combination which is familiar to us right from linear regression. And we apply nonlinear activation on this linear combination to obtain the label y. And this label y is either +1 or -1. Let's look at these individual components. So y is the label, x is the feature vector, phi is the feature transformation. So we apply feature transformation on the feature vector and obtain a new feature representation. This is a generic way of writing the features. Then we have a weight vector, we have a nonlinear activation function, and W transpose phi of x is a very familiar linear combination of features. So this is how Perceptron model looks like. This is a very generic model that will recur in different classification schemes where we'll be using different nonlinear activation functions. However, in case of Perceptron, f, which is a nonlinear activation function, we use sine or a threshold function. So let's say this linear combination is z. So in order to calculate f of z, we calculate it as follows. So we assign +1 to f of z if z is greater than or equal to 0, and we assign -1 otherwise, that is z less than 0. So we can write y as sine of linear combination of features. This is a compact way of writing it. So instead of f, this f we replaced with sine, which is the nonlinear activation function that we are using in case of Perceptron. Let's look at how this function looks like. So in this function, the value of, whenever the value of x is less than 0, then we have y equal to -1. And this in fact is a linear combination. This label is a bit misleading. This is actually a linear combination when the value of the linear combination, which is z, which is here represented by x. So if the linear combination is less than 0, we have y equal to -1. And when the value of linear combination is greater than or equal to 0, we have y equal to +1. So in a sense, it's like a step function. Now that we have seen the model of perceptron, let's look at the third component, that is loss function. So in order to calculate loss function, as you already know, we take prediction from the model and we compare it with the actual label, and then we calculate the loss based on the difference in the prediction and the actual label. Let's look at how to compute loss in case of perceptron. So let's say the predicted label, which is y hat, for ith example, it will be either -1 or +1, and the actual label is yi. Then we calculate error as follows. So the error is 0 if both the prediction and actual label match, and if they don't match, the error is essentially negative of the linear combination multiplied by the actual label. So it is minus W transpose phi of xi into yi. So that is the error whenever we have a misclassification. So you can see that for correctly classified examples, the error is 0, and for misclassified example, the error is minus W transpose phi of xi yi. So we can write this error compactly as error is max of 0, comma minus W transpose phi of xi yi. So this is a linear combination. W transpose phi of xi is a linear combination multiplied by the label of the ith example. So we can replace this linear combination by hw of xi, which is the model, is a perceptron model that returns the prediction, and we multiply that with the value of the label. So ei is max of 0, comma minus hw of xi yi. Let us illustrate the loss function. So hw of xi is either -1 or +1, that is the prediction, and if the decision is correct, then we have both the predicted label and actual label equal to either +1 or they are -1. So let's see what happens when both the labels are +1. So we simply substitute the values of the predicted label and actual label in the equation for the error. Error is max of 0, comma minus hw of xi yi, and we substitute these values. The predicted value is +1, actual value is +1, so we get max of 0, comma -1, which is 0. So you can see that for this correctly classified case, we are getting 0, and we can verify the same with the other side where both the prediction and actual labels are -1. So you can see that here it is max of 0, comma predicted value into actual value. So we have max of minus of -1 into -1, which is +1, and this minus comes here, so it is 0 and -1, max of 0, comma -1, which is 0. So you can see that in both the cases, when the decision is correct, we are getting error of 0. Now let's look at the case when we have a misclassification at hand. That is, the decision is wrong. Then we have, let's say, the predicted value as +1 and actual value of -1. Or the other case where the predicted value is -1 and actual value is +1. In the first case, where the prediction is +1 and actual value is -1, we can see that we get into a situation where we have max of 0, 1, so we get error of 1. In the other case, we end up with max of 0, 1, which is 1, by substituting the values of the prediction and the actual label. So we get max of 0, 1, which is 1. So you can see that in both the cases, the error is 1 when the decision is wrong, or when we have a misclassification at hand. So that was the error at individual example. We simply sum up the error across all n examples or across all n samples. So we have the loss, which is j of w, which is sum over all n example max of 0 comma minus yi into the prediction, which is hw of xi. So this particular equation inside is exactly how we calculate the error for ith point, as we have seen on the previous slides. So the error is a piecewise linear function. It is 0 in the correctly classified region, and it is a linear combination. It is a linear function of w in the misclassified regions. So jw is not differentiable in w. So let's look at how this loss function looks like. So on x-axis, we have the value of prediction into the actual label, and you can see that in the correctly classified region we have the value of loss as 0, and in the incorrectly classified region the loss is a linear function of w, or in other words, loss is directly proportional to w. Thus for misclassified example, we can reduce loss by reducing w. If you reduce w, the loss will automatically reduce. And for correctly classified examples, we leave the value of w unchanged because we have achieved a 0 loss in case of correctly classified region. Now that we have seen the loss function, the next task is to obtain the weight vector that minimizes the loss. Now we'll look at the optimization procedure used in Perceptron, and this procedure is known as Perceptron update rule. So let's look at Perceptron update rule. We initialize the weight vector to 0, and for each training example, we calculate we first perform the prediction, or we get the prediction from Perceptron by simply applying the Perceptron model, which is a signature of the linear combination. And what happens is, based on this predicted value, we calculate the updated value of w at time t plus 1, and this w is set to the value of w at the current timestamp, that is w at t, plus alpha is the learning rate, alpha times the difference in the prediction, which is, this is the actual prediction, this is the actual label, and this is the predicted label. So we calculate the difference between the actual label and the predicted label. We multiply it by the feature, by the feature vector. So you can see that for correctly classified examples, this particular quantity, which is the actual label minus the predicted label, is 0, and hence there is no change in the weight vector because we are simply having a 0 here. So if we multiply the remaining rest of the terms with 0, so we end up with 0 in this particular part. So that will result into w at t plus 1 equal to w at t. So if we have linearly separable examples, we have a training set where two classes are linearly separable, then Perceptron procedure converges. It converges with 0 loss. If we do not have that case, if we do not have linearly separable examples, then Perceptron procedure does not converge. Instead, it oscillates. Let us understand Perceptron update rule for various values of the predictions. So we set the next value of the w to the current value plus learning rate times the difference in the actual label and predicted label multiplied by the feature vector for ith example. So for correctly classified case, we have prediction equal to, we have the predicted label equal to the actual label, and in that case, if we substitute, if we can see that since these two things are equal, the difference becomes 0, and since the difference becomes 0, we essentially add 0 to the value of the current weight vector. So in that case, the next value of the weight vector does not change. It is exactly as the current value of the weight vector. So in case of correctly classified case, we do not change the weight vector. Let's look at a couple of misclassification cases. The first one is a negative class misclassification where the actual label is -1 but it is predicted to be +1. If we substitute these values in this equation, we get the new value of W as the current value minus twice the learning rate into the feature vector. And in case of positive class misclassification, we essentially change the weight vector to the current weight vector plus twice the learning rate into the feature vector. So in case of Perceptron, we process examples one by one, and for each example we check what is the prediction, and based on the prediction we essentially update the weight vector. And as you can see, in the correctly classified case, the weight vector remains unchanged. In case of negative, in case of misclassification, if you are having a negative class misclassification, the weight vector is changed by subtracting twice the learning rate times the feature vector from the current value of the weights to get the updated weight vector. In case of positive class misclassification, we update the weight vector by adding twice the learning rate times feature vector to the current value of the weight vector to obtain the new weight vector. So you can see that on linearly separable data, the optimization procedure eventually converges. So you can see that this is the wrong classification, then the weight vector is updated. For every wrong classification, the weight vector is updated. So you can see this demonstration where they look at individual example. Whenever there is a wrongly classified point, they end up changing the weight vector, and because we are changing the weight vector, it ends up changing the decision boundary between two classes. Let's look at the demonstration of optimization procedure for linearly separable case. So you can see that on linearly separable data, the optimization procedure converges and the loss gradually reduces. But in case of non-separable case, so here two classes are not separable. So in this case, the optimization procedure does not converge, but instead it oscillates. Instead the loss oscillates. It comes down, then it goes up, and it is never able to converge. So that is sort of disadvantage of Perceptron procedure. So we generally do not use Perceptron because there are more advanced machine learning algorithms for classification, but Perceptron has historical importance, and Perceptron is also used as a starting point for understanding machine learning from a theoretical perspective. And Perceptron algorithm, even if it looks like linear regression or other algorithms like logistic regression, it is actually a very different algorithm because the output label of Perceptron, we cannot actually assign a probabilistic interpretation to it. So in that sense, Perceptron is a very different classification algorithm. Finally, let's look at the evaluation metrics of Perceptron, and these evaluation metrics that we use here are exactly same as any other classification algorithm. So we first calculate confusion matrix based on predictions, based on predicted and actual labels, and based on this confusion matrix we calculate quantities like precision, recall, accuracy, and F1 score. Let's look at the confusion matrix. Example of a confusion matrix. So here on confusion matrix we have predicted label on one side and actual label on other side. We have there are these labels, actual predicted labels, and these are actual labels, and we calculate cases where these things matches. So for example, predicted label is -1, actual label is -1. So here we count how many cases we have, both of them as -1. So this is a correctly classified case because both the labels match. Both the labels also match in this particular case, where and we calculate how many examples this particular situation occurs where both of the labels matches. So on diagonal we essentially have correctly classified examples, and off diagonal elements essentially capture the number of misclassified examples in different cases where the predicted label is, where the actual label is -1, but we end up predicting label as 1. So those misclassifications are recorded here, whereas actual label is +1, but whenever we predict -1, that type of misclassification is captured in this particular cell. So you can see that these are true positives. We have 25 true positives, we have 25 true negatives, we have 0 false positives and 0 false negatives. So this is an ideal confusion matrix. So based on this confusion matrix, we calculate the value of precision, and precision is true positive by true positive plus false positive, and by substituting these values here we get a precision of 1. In our case, in this particular case, the negative class is a positive class for us, is a positive prediction for us, and this +1 is a negative class. So in that sense, we have, these are two positives, these are two negatives. Then we have recall, which is a ratio of true positives to true positives plus false negative, which again is 1. And F1 score is a harmonic mean of precision and recall, and F1 score is also 1. So this is of course an ideal case of classification, and we should strive to get to this kind of a confusion matrix, but it may not be possible in all the situations in real life. We will have some misclassification, but our objective should be to reduce the misclassifications as far as possible. That's it from Perceptron. In the next video, we'll implement Perceptron from scratch in Colab. Thank you and Namaste.